Hello, my dear students. Welcome to the session continuation of important observations from our electronics concepts. In this session, with respect to Module 2, rectifiers, that is AC to DC converters, I would like to discuss about concept of single phase full wave or fully controlled rectifiers. All of you concentrate. Students, we know that in single phase full wave or fully controlled rectifiers, there is a two types of configurations. One is bridge configuration, another one is midpoint configuration. It may be bridge rectifier or midpoint rectifier. The analysis and waveforms are same except number of devices, weak inverse voltage and transformer utilization. In the explanation of full wave rectifiers or fully controlled rectifiers, I will explain only bridge rectifiers. The same formulas are applicable for midpoint type rectifiers. And one more point you have to remember here, single phase bridge configuration is also called B2 configuration. That is, B indicates bridge configuration, 2 indicates number of pulses per cycle. Single phase midpoint type rectifier configuration is also called M2 configuration. M indicates the midpoint configuration, 2 indicates the number of pulses per cycle. First we have to start with the single phase full wave or fully controlled bridge rectifier using R load. And one more point you have to remember, students. In full wave rectifiers, R and RE load, it is a discontinuous mode. Remaining loads, RL load, RL and freewheeling diode, RLE load, RL and freewheeling diode, continuous mode of operation. Unless otherwise specified, you have to take like this only. R load, RE load always discontinuous mode. RL load, RL and freewheeling diode, RLE load, RLE and freewheeling diode, continuous mode of operation. If they given discontinuous mode, then only you take discontinuous mode. If it is not specified for these loads, you have to take the continuous mode only. First, we'll start with the single phase fully controlled bridge rectifier using R load. Fully controlled bridge rectifier or full wave bridge rectifier. Both are same state. But you have to concentrate. Here we are using 4 thyristors. Positive off cycle T1, T2 will conduct. Negative off cycle T3, T4 will conduct. T1, T2 conducts alpha 2 pi. Then SCR conduction angle is pi minus alpha. T3, T4 will conduct negative off cycle pi plus alpha to 2 pi. Then here also each SCR conduction angle is pi minus alpha. But I told already, mainly for rectifiers, you have to concentrate instead of waveforms. These are the waveforms for single phase, full wave or fully controlled rectifier using R load. How many pulses per cycle here? Per cycle 2 pulses. That's why it is also called 2 pulse converter, whose ripple frequency is 2f square. This is the output voltage and output current waveform. This each thyristor current waveform. This is the source current waveform. But very important is analysis point. For single phase, full wave or fully controlled bridge rectifier using R load, what the peak inverse voltage? In bridge configuration, always peak inverse voltage is Vm. The circuit turn off time pi by omega. Each SCR conduction angle pi minus alpha. What the average output voltage? This is important. V naught equal to Vm by pi into 1 plus cos alpha. It is half wave controlled rectifier Vm by 2 pi into 1 plus cos alpha. But here Vm by pi into 1 plus cos alpha. That is 2 times. As compared to half wave rectifier, in full wave rectifier, the output, average output voltage is 2 times. This is average output current expression. This is RMS output voltage. This is also very important formula. That is Vm by root 2 pi. But in half wave rectifier, 2 root pi. But here root 2 pi into pi minus alpha plus 1 by 2 sine 2 alpha whole to the power of 1 by 2. This is RMS current expression. This output power. This is also very important. The output power equal to V naught RMS square by R. What are the input power factor, students? V naught RMS by Vs. Source current waveform is sinusoidal. That is for resistive load. Single phase full wave rectifier or fully controlled rectifier, resistive load source current is sine wave. But for inductive load, without freewheeling diode case, source current is square wave. With freewheeling diode case, source current is quasi square wave. That is in full wave rectifier, 3 types of waveforms are exist. Source current waveforms that are already given at the starting of rectifier. This is the average thyristor current. With respect to each thyristor, it acts as a half wave rectifier. You see in the waveform also. With respect to each thyristor, it is which output? Half wave rectifier output. That's why this is the average thyristor current expression. This is RMS thyristor current expression. But one point you have to remember, students. In this circuit, this is the full wave or fully controlled rectifier using R load. In this circuit, during the operation, let assume that this T3 thyristor is damaged and open circuit. If any one thyristor is damaged and open circuited, it acts as a half wave rectifier. Then once it acts as a half wave rectifier, what the average output voltage formula? That is Vm by 2 pi into 1 plus cos alpha. This is the observation. The question is asked like this. Single phase full wave or fully controlled bridge rectifier using R load. During the operation, if any one thyristor is damaged and open circuited, what the average output voltage? That is, it acts as a half wave rectifier. That's Vm by 2 pi. Actual average voltage is Vm by pi, but here Vm by 2 pi because it acts as a half wave rectifier. Then this is a single phase fully controlled midpoint type rectifier using R load. It may be bridge rectifier or midpoint type rectifier. Same formula, same waveform, same analysis. Only difference is number of devices are different. Peak inverse voltage is different. Transformer utilization factor is different. That's why the average output voltage is same. Vm by pi into 1 plus cos alpha. The conduction angle is also same. Pi minus alpha. The analysis and waveforms of single phase full wave, fully controlled midpoint type rectifier and similar to bridge rectifier using R load. That point you have to remember, except to peak inverse voltage. But here the peak inverse voltage is how much, friends? 2 Vm. But in bridge rectifier, what is the peak inverse voltage? That's Vm. Yeah, this problem you have to practice. Here it is given single phase full wave bridge rectifier supplying power to a resistive load of 10 ohms. Firing angle is given 90 degrees. If the supply voltage is 200 volts 50 hertz, calculate average output voltage. In full wave rectifier, average output voltage is Vm by pi into 1 plus cos alpha. Substitute firing angle 90 degrees, we are getting average output voltage. You have to calculate average output current, students. Then if it is asked what the output power, to calculate output power with respect to resistive load, first we have to calculate RMS value. Once you know the RMS voltage, substitute here, then we can get the expression for output power. And what is the input power factor? V naught RMS by Vs, that I am getting 0.707 lakh. Please practice these questions. Once again, I am repeating this statement. You follow the whatever the analysis points I given and solve this practice code. That is only our final preparation with respect. And one more question that I framed here, that is with respect to midpoint type rectifier. That I told already, sometimes they will give the turns ratio. If the turns ratio is given, whatever the voltage they given, directly don't take the secondary voltage. You have to take the primary voltage. From that primary voltage, you have to calculate the secondary voltage. Once you know the secondary voltage, that voltage only you have to substitute in the formulas. This is the maximum value, but it is the RMS value. Then how to substitute maximum value? Root to RMS value. Then by substituting that, we are getting the average output. But here asking that what the maximum average output. But in this problem, firing angle is not given. But it is asking that what the maximum average output voltage. How to get the maximum average output voltage? By substituting firing angle equal to 0 degrees. That I told. When the average output voltage is maximum for alpha equal to 0 degrees. One more question. You have to calculate the alpha for load voltage of 100 volts. If the average voltage is 100 volts, calculate the firing angle. The peak inverse voltage is 2 Vm. These models of questions you have. And one more configuration of single phase fully controlled bridge rectifier or full wave bridge rectifier, that is using RE load. R load and RE load both are discontinuous mode of operation. Discontinuous mode battery, minimum angle at which the SCR will be triggered, theta 1. That is theta 1 equal to sine inverse E by Vm. In this case, the thyristor conduction angles are theta 2 minus alpha because it conduct alpha to theta 2. These are the waveforms, but no need to practice the waveforms with respect to rectifiers. Mainly you have to concentrate on the analysis. Then what is the peak inverse voltage Vm? The circuit turn off time is pi plus 2 theta 1 by omega. Each SCR conduction angle is theta 2 minus alpha. That is alpha to theta 2 means theta 2 minus alpha. Then what is the average output current, student? This is the average output current expression. You have to use this formula, or I will give the direct formula also. From that formula also directly you can calculate. This is the average output voltage formula, but no need to practice the RMS output current formula. This is the output power, input power factor. Direct formula you have to remember. The average source current is 0. Then RMS source current equal to RMS load current. I told already during the operation, if any one thyristor is damaged, it acts as a half wave rectifier. Once it is a half wave rectifier, current becomes 1 by 2 times. Current becomes 1 by 2 times. That is, in single phase half wave control rectifier, this is the I naught of half wave rectifier. And this is the I naught of full wave rectifier. I naught of full wave rectifier equal 2 times of I naught of half wave rectifier. This direct formula that you have to remember. That is, to calculate the average load current, use this formula. Or if you are feeling the integration is very difficult like that you are feeling, then directly you have to use this formula and substitute. But this gamma is in radians. This gamma value you have to substitute in radians. That is observation. That observation is one. Single phase, full wave or fully controlled midpoint type rectifier RE load, peak inverse voltage is 2 Vm. That point also you have to concentrate. But the average output voltage V naught equal to E plus I naught into R. This is for R load and RE loads. And you have to practice this model of question. Mainly very important for 2 marks model, I naught is asking that I naught. I naught equal to how much? Average load current. You can also expect circuit turn off time. The circuit turn off time T is equal to pi plus 2 theta 1 by omega. Next, very important configurations of single phase, full wave or fully controlled rectifiers, that is RL load. But point you have to remember, students, it may be RL load or RLE load. Same waveforms and same analysis, except one formula. For this case, I naught equal to V naught by R. For this case, I naught equal to V naught minus E by R. If the battery is present, I naught equal to V naught minus E by R. Then remaining formulas, waveforms, it may be RL load is given or RLE load is given. Even conduction angles also, all are equal. But assuming that it is a which mode of operation? Continuous mode of operation. But what do you mean by continuous mode of operation? Continuous mode means in one cycle without current zero, if the current is applied to the load, that is nothing but a continuous mode of operation. If you have to operate the circuit in continuous mode of operation, what are the assumptions? Load must be consist of large inductor. These are the assumptions to operate in continuous mode. Outgoing SCRs must be conduct up to incoming SCRs are turn off. That is, whatever the SCRs are going to turn off, those SCRs must be conduct up to next pair of the resistors will conduct. And beta must be greater than or equal to pi plus alpha. That is, minimum angle of beta is pi plus alpha. If beta is pi plus alpha, then it is a continuous mode. Beta equal to pi plus alpha, it is a continuous mode. If beta less than pi plus alpha, it is a discontinuous mode. Even though load consists of battery, there is no concept of theta 1 and theta 2. If you consider theta 1, theta 2, it becomes a discontinuous mode. But you have to operate in continuous mode. That's why there is no concept of theta 1, theta 2. In a continuous mode, even though load consists of battery, the minimum angle at which SCR is triggered is 0 degrees. You can also trigger 0 degrees. Then small firing angles are preferable. In continuous mode for RL load and RLE load, same analysis and same waveforms except I naught. I told already for RL load I naught equal to V naught by R. For RLE load I naught equal to V naught minus E by R. These are the assumptions during the operation of continuous mode. Then what is the operation for RLE load? Positive half cycle T1, T2 will conduct. Negative half cycle T3, T4 will conduct. But T1, T2 conduct this is in continuous mode of operation. T1, T2 conduct alpha to pi plus alpha. T3, T4 will conduct pi plus alpha to 2 pi plus alpha. Then each SCR conduction angle is pi. If it is a discontinuous mode, I already given this statement, students. Unless otherwise specified, full wave rectifier with inductive loads, always you take the continuous mode. If they specified discontinuous mode, then only you take the discontinuous. In discontinuous mode of operation, T1, T2 will conduct alpha to beta, T3, T4 will conduct pi plus alpha to pi plus beta, then SCR conduction angle is beta minus alpha. But here each SCR conduction angle is pi square. That you have to concentrate. And these are the waveforms with respect to continuous mode of operation. This is the average output voltage, that is output voltage waveform. And this is the output current waveform. Let us assume that we are supplying the constant current to the load. Simply we can draw the one straight line also, that is also correct. And this is the source current waveform. Source current waveform is the square waveform. A full wave rectifier without freewheeling diode case in inductive loads, it is a square waveform. Mainly you have to concentrate on the analysis points. And here I given the each thyristor current waveform, voltage across the thyristor waveforms also I given. Mainly source current waveform is very important. And then finally you have to concentrate on the analysis. Waveforms we don't expect. Maximum we can expect on the analysis point. The single phase, full wave or fully controlled rectifier, RL load or RLE load, all the formulas are same. Peak inverse voltage Vm, this is important. A full wave rectifier without freewheeling diode case, the circuit turn off time in RL load and RLE load, phi minus alpha by omega. Even with freewheeling diode case also we can get phi minus alpha by omega. How much angle each SCR will conduct? Without freewheeling diode case, each SCR conduction angle is 180 degrees. But with freewheeling diode, each SCR conduction angle is 180 minus alpha. You can. That you will see later on. Then what the average output voltage? This is very important. In continuous mode of operation, in full wave rectifier, the average output voltage is 2 Vm by pi into cos alpha. Then what the average load current? RL load V0 by R, RLE load V0 minus E by R. What is the RMS output voltage? This is very important 5-star gunshot question. This is the expected model. In full wave rectifier continuous mode of operation, simply remember the RMS voltage is equal to Vm by root 2. There is no any firing angle, all this. By simplifying, we are getting RMS voltage is equal to Vm by root 2. Then what is the output power? V0 equal to V0 into I0. In a continuous mode, you have to take the average values. What is the RMS output current, students? In a continuous mode of operation, I0 RMS equal to I0 only. Source current is a square waveform. Average source current is 0. RMS source current equal to I0, students. Full wave rectifier, RMS source current equal to I0. Very important observation. What is the average value of each thyristor current? Average value of each thyristor current equal to I0 by 2. What is the RMS value of each thyristor current, students? I0 by root 2. What is the input power factor? That input power factor equal to V0 into I0 by Vs into Is. But you know that Is equal to I0. That's why V0 by Vs. Simply remember input power factor equal to V0 by Vs. The RMS source current, RMS load current equal to average load current equal to RMS source current. In full wave rectifier, it may be diode rectifier or it may be thyristor rectifier. Full wave rectifier continuous mode of operation. All these currents are equal to RMS load current equal to average load current equal to RMS source current. In continuous mode, during operation, if any one SCR is damaged and open circuited, what the average output voltage? Vm by pi into cos alpha. During operation, if any one SCR is damaged and open circuited, the average output voltage is equal to Vm by pi into cos alpha. These are the observations with respect to single phase full wave or fully controlled bridge rectifier using RL load and RLE load. And this problem you have to practice. We may expect what the average output voltage, what the average output current, what the RMS output voltage, what the output power, what the average source current and RMS source current, what the RMS load current, what the average thyristor current, what the RMS thyristor current, what the input power factor. This is the expected models of questions with respect to single phase, full wave or fully controlled bridge rectifier, either RL load or RLE. Only RL load and RLE load current formula. RL load V0 by R. RLE load V0 minus E by R. This is RLE load case. Here it is asking that what is the average output current. Average output current if one of the SCRs gets damaged, open circuited. If one of the SCR is damaged, V0 equal to Vm by pi into cos alpha. Then V0 equal 45 volts. Then I0 equal V0 minus E by R 2.5 ampere. That you have to concentrate. For single phase full wave or fully controlled midpoint type rectifier, if RL load is given, RLE load is given. Same formulas. Here also V0 equal to Vm by pi. I told already, students. For midpoint type rectifier, bridge rectifier, formulas are same except peak inverse voltage, number of thyristors, that is number of devices, and the transform utilization factor. The analysis and waveforms are same that of single phase bridge rectifier. Again, no need to draw the waveforms, all the formulas. This is applicable for midpoint and bridge is same. One more very important concept with respect to full wave rectifier. These formulas are applicable for both midpoint and bridge rectifier. These formulas are applicable for both midpoint and bridge rectifier. What the input performance parameters are input harmonic analysis of single phase full wave. This is specially given in the GATE syllabus. Input harmonic analysis or input performance parameters of single phase full wave rectifiers. Friends, we know that in full wave rectifier, it may be midpoint type rectifier or bridge rectifier. The source current is square wave. It is a square wave means it is a sinusoidal or non-sinusoidal. It is a non-sinusoidal. Any non-sinusoidal waveforms are analyzed by using Fourier series. That's why for this waveform we have to apply the Fourier analysis. It is a square wave. It is analyzed by using Fourier series. If you apply the Fourier analysis, then this is the representation of instantaneous current expression. Then you have to calculate A0, AN and BN values for the square waveform. Then if you calculate A0 equal to 0. This is also important. Sometimes they will ask A0, AN, BN values also. This is the AN values. This AN is exist only for odd harmonics. For all the even harmonics, it is 0. Even Bn is also exist only for odd harmonics. For all the even harmonics, it is 0. This is An value. This is Bn values. Once you know A0, An and Bn values, you have to substitute. By calculating A0, An and Bn values, you have to substitute in instantaneous current expression and simplify that. We can get the source current. The source current expression is summation n equal to 13135 up to infinity. N equal to 135 up to infinity. 4 I naught by n pi sin of n omega t minus n alpha. By knowing this source current expression, sometimes in the gate exam, direct this equation also we can expect. Direct formula also we can expect. Ready to answer. This is the instantaneous source current formula. By knowing this instantaneous source current formula, here I given some derivation part that you have to concentrate. Here directly I given the statement. According to that statement, I simplified here. This is the source current expression. But what is the observation here? The input current or source current consists of only odd harmonics. There is no any even harmonics. Important observations. In single phase full wave rectifier, the input current or source current consists of only odd harmonic. Once it consists of only odd harmonics, which is the most dominant harmonic? Third harmonic is the most dominant harmonic. Then what is the order of harmonic? The order of harmonic equal to 2k plus 1. That is 3, 5, 7 and so on. That is the input source current waveform, which harmonics it consists. And this important observation that you have to concentrate. Type of converter, input side harmonics, output side harmonics. In 2-pulse converter is a single phase full wave rectifier. In 2-pulse converter, input side harmonics are 2k plus 1, output side harmonics are 2k harmonics. That is, in 2-pulse converter, input side most dominant is third order, output side most dominant is second order. In 6-pulse converter, what is the input side harmonics? 6k plus or minus 1 harmonics. What is the output side harmonics? 6k harmonics. Output side means DC side. Input side means AC side. Because in rectifiers, input is AC, output is DC. That is, in 6-pulse converter, which is the most dominant harmonic at input side, 5th order. In output side, which is the most dominant harmonic, 6th order. Important observation, students. In a 12-pulse converter, what is the input side harmonics? 12k plus or minus 1. What is the output side harmonics? 12k harmonics. Which is the most dominant harmonic in 12-pulse converter at input side? 11th order. Which is the most dominant harmonic at output side? 12th order. For p-pulse converter, then what is the order of harmonic? Pk plus or minus 1 students. That is input side harmonics. Output side harmonics are pk. This is the very important observation. Even in HVDC converters point of view also, these observations are very important. These are the harmonics at input side and order of harmonics at input side and output side, and which is the most dominant harmonics at input side, which is the most dominant harmonics at output side. Then these are the input performance parameters. Once you know the instantaneous current expression, of single phase full wave rectifier, then how to write the different formulas? Displacement angle. Nth order displacement angle is n alpha. Fundamental displacement angle is alpha. What the displacement factor? This is fundamental displacement factor is important, students. Cos alpha. Many times the questions are framed in gate exam. In a single phase full wave or fully controlled bridge rectifier or midpoint rectifier, both the cases it is applicable. Then what is the displacement factor? Displacement factor equal to cos alpha. Fundamental. If third order, cos 3 alpha. Fifth order, cos 5 alpha. Only odd harmonics only possible. What the maximum value of nth order harmonic current, students? 4 I naught by n pi. Every formula is important. What the maximum value of fundamental current? Replace n equal to 1. 4 I naught by pi. What is the RMS value of nth harmonic source current? 2 root 2 by n pi into I naught, students. What is the fundamental current? RMS value of fundamental source current. Many times already different competitive exam it is framed. Even gate exam also 1 or 2 times it is framed. RMS value of fundamental source current of single, all these formulas for single phase full wave rectifier. Then what is the RMS value of source current? RMS source current is I naught. This is the fundamental source current, 0.9 times of I naught. But source current is I naught. Then what is the current distortion factor? IS1 by I naught, that equals 0.9. What is the current distortion factor of full wave rectifier? 0.9. What is the total harmonic distortion? You know the formula of total harmonic distortion? 1 by current distortion factor square minus 1 whole to the power of 1 by 2. CDF I calculated 0.9, that you substitute here. This we are getting 48.43%. Direct values also you can express. That is in a single phase full wave rectifier, current distortion factor is 90%. Total harmonic distortion is 48.43%. Total harmonic distortion is 48.43%. Then what is the input power factor? This is also very important 5-star form. For a single phase full wave rectifier or fully controlled rectifier, it may be midpoint or bridge rectifier. Both the cases these formulas are applicable. The input power factor equal to 0.9 into cos alpha. Many times based on this formula questions are there in gate exam. Simply they will give the firing angle and it is asking that what is the input power factor. You have to use 0.9 cos alpha. Then what is the active power input formula, students? Active power input equal to V naught into I naught. This is derivation part also I can. Please go through this. But the reactive power input equal to V naught I naught tan alpha. Very important formula, students. Active power input, that is how much power, how much active power supplied to the converter, V naught into I naught. How much reactive power supplied to the full wave rectifier, that is V naught I naught tan alpha. Then what is the relation between reactive power, active power and firing angle? Still now not framed, but this is the most expected model of question from this formula, students. We can expect in the next coming gate exams. From this, they will give the reactive power and active power, calculate the firing angle. Or they will give the firing angle and active power, calculate the reactive power. This is very important observation that you have to concentrate. This is about the input performance parameters of single phase full wave rectifier. These formulas are applicable for both midpoint and bridge rectifier. This one simple model of question repeated in gate exam. Simply they are asking by giving the firing angle, they are asking what is the input power factor. Input power factor equal 0.9 cos alpha. Then 0.9 cos alpha, alpha 30 degrees cos 30 root 3 by 2, that is 0.78. Sometimes they will ask what is the displacement factor. Displacement factor is cos alpha. Power factor is 0.9 cos alpha. Next is the expected models of questions. You have to practice these questions. We may expect what is the average voltage and average current. What is the RMS voltage and RMS current? What is the source current, RMS source current, fundamental source current, average source current, displacement factor and input power factor, active power input and reactive power input, what is the firing angle if they given the active and reactive power. This average output voltage formula 2 Vm by pi cos alpha, average current RLE load V naught minus E by R, RMS output voltage Vm by root 2, RMS source current is I naught, RMS value of fundamental source current is 0.9 times of I naught, average source current. This is expected, students. This model of question you have to practice. What is the displacement factor cos alpha? What is the input power factor 0.9 cos alpha? What is the active power input V naught into I naught? Reactive power input V naught I naught into tan alpha. They given reactive power and active power, it is asking that firing angle. We are getting 30 degrees. These are the expected models of questions with respect to single phase full wave or fully controlled bridge rectifier or midpoint type rectifiers. Both the cases these formulas are applicable. But I told already, in a continuous mode of operation, during operation, if any one thyristor is damaged and open circuited, then average output voltage is reduced by 1 by 2 times. Then average output voltage is equal to Vm by pi into cos alpha. Based on this problem also already solved. But in a single phase fully controlled rectifier using RL load or RLE load, in a continuous mode of operation, each SCR conduction angle is pi. But in discontinuous mode of operation, each SCR conduction angle is beta minus alpha. One more important concept with respect to full wave rectifier or fully controlled rectifier, it may be midpoint or bridge rectifier, students, what is the quadrant operation. Friends, we know that the average output voltage in the case of full wave rectifier is 2 Vm by pi into cos alpha. You substitute any firing angle for alpha less than 90 degrees. That is 0 to 90 degrees, V naught is positive. In rectifiers, current never be negative. Why current never be negative? Current negative means, see for example, this is the rectifier, students. This is the rectifier circuit. Current negative means the current is flowing like this. That is meaningless. That is, thyristors cannot allow the current in the reverse direction. That means in rectifiers, the current never be negative. Voltage may be positive or negative based on the type of rectifier. But in any rectifier, current is always positive. That is, for alpha less than 90 degrees, V naught positive, I naught positive, then first quadrant. That is, full wave rectifier for alpha less than 90 degrees, it is operated in the first quadrant. For alpha greater than 90 degrees, that is for 90 to 180 degree firing angle, V naught you can get the negative, I naught is always positive, then which quadrant? Fourth quadrant. That is, single phase full wave rectifier or fully controlled rectifier, it is a 2 pulse 2 quadrant converter. It is a 2 pulse 2 quadrant converter. In which quadrant it is operating? First quadrant and fourth quadrant. First quadrant and fourth quadrant it is operating. That is, for alpha less than 90 degrees, V naught positive, I naught positive, power positive. For alpha less than 90 degrees, power is positive means power is delivered from source to load, AC to DC. That is, for alpha less than 90 degrees, it is operating rectifying mode and it is used only for forward motoring current. This is observations. This also asking in gate exam. V naught less than 0, I naught less than 0, V naught greater than 0, I naught greater. That type of options also giving. That is, in full wave rectifier, alpha less than 90 degrees, V naught greater than 0, I naught greater than 0, first quadrant, rectifying mode, forward motoring. Full wave rectifier for alpha greater than 90 degrees, alpha greater than 90 degrees, V naught less than 0, that is voltage is negative, current is always positive, then it is reverse braking mode of operation, it is a inverting mode. That is, for alpha greater than 90 degrees, power is delivered from load to source. This is important. We know that in rectifiers, load is DC, source is AC, power is delivering from DC to AC. That's why it is acting as an inverter. Actually, it is not an inverter circuit. It is not an inverter circuit, sir. It is a rectifier circuit only. But alpha greater than 90 degrees, power is delivering from DC to AC. That's the reason why it is an inverting mode of operation. Even though it is not a inverter circuit, it is a rectifier circuit, but it is operating as an inverter. That's why these inverters are called line commutated inverters. Because in rectifiers, which commutation we can use? Line commutation. That's why rectifier acting as inverter. In rectifiers, we can use the line commutation. That's why these inverters are also called line commutated inverters. That means what is the point you have to remember here, friends? Line commutated inverters, actually it's not inverters. It is a rectifiers. But alpha greater than 90 degrees, rectifier act as a. Then here I am telling that alpha less than 90 degrees, V naught is positive. Alpha greater than 90 degrees, V naught negative. Sir, why it is positive and negative? This is the reason. If you draw the any waveform for alpha less than 90 degrees, always average voltage if you take. Positive area is greater than the negative area, average voltage is positive. This is the reason why for alpha less than 90 degrees, V naught is positive. For alpha equal to 90 degrees, V naught 0. For alpha equal 90 degrees, V naught 0. Why? For alpha equal 90 degrees, V naught 0, positive area equal negative area. If you draw the waveforms for alpha equal 90 degrees, this is the waveform. For alpha greater than 90 degrees, negative area is greater. Negative area is greater than the positive area. That's the reason why we are getting V naught equal to negative. These observations also very important with respect to quadrant. Then, what are the control characteristics of full wave rectifier or fully controlled rectifiers? We know that the average output voltage of full wave rectifier or fully controlled rectifier V naught equal to 2 Vm by pi cos alpha. Substitute alpha 0 degrees, we can get 2 Vm by pi. Substitute alpha 90 degrees in this formula, we can get V naught 0. Substitute alpha equal to 180 degrees, we are getting minus 2 Vm by pi. That is, if we control the firing angle from 0 degrees to 180 degrees, the average output voltage is controlled from 2 Vm by pi to minus 2 Vm by pi square. That is the output voltage is controlled from positive to negative if you control the firing angle from 0 to 180 degrees. This is the control characteristics of a single phase full wave rectifier, maybe midpoint type rectifier or bridge rectifier. Now the question is, I told already, for alpha greater than 90 degrees, power is delivered from load to source. Sir, is it practically possible to deliver the power from load to source? Yes, it is possible, but there must be some conditions are satisfied. That is, to deliver the power from load to source or to operate as a line commutated inverter. then which conditions must be satisfied? It must be a full wave rectifier operate in continuous mode. Then only power is delivered from load to source. Alpha must be greater than 90 degrees. Firing angle must be 90 to 180 degrees. Load must be consist of battery or equivalent back. Generally, it must be consist of battery. Battery is not present, there must be back EMF. Why? Because DC motor is one of the example of RLE load. That's why if it's a motor concept, you have to use the back EMF. And battery terminals must be interchanged. This is important. It must be consist of battery. You must interchange the battery terminals. That is, during the power is delivered from load to source, how to write the expression for V naught? V naught equal to minus E plus I naught into R square. This is also very important. Based on this formula also, gate question already framed. During the power is delivered from load to source. During the power is delivered from load to source, the average output voltage is equal to minus E plus I naught into R. That is battery. Why negative sign I taken? Because battery terminals are. In general, a full wave rectifier without freewheeling diode is more preferable practical. Why? Because without freewheeling diode only, it is operated in the motoring mode and braking mode. Yeah, this question you have to practice. A single phase AC to DC control rectifier operate in regenerative mode. Which of the following conditions should be satisfied? It must be full wave rectifier. Alpha must be greater than 90 degrees. Source of EMF in the load. Must be fully controlled rectifier. Alpha must be greater than 90 degrees. Source of EMF in the load. Then only power is delivered from source and it is operating in the regenerative braking mode. And this problem also you have to practice. If the power is delivered from load to source, power is delivered from load to source, what the firing angle it is. If the power is delivered from load to source, V naught equal to, don't use E plus I naught, or you can use the minus E plus I naught. Then what is V naught? 2 Vm by pi cos alpha. Substitute this. From this, we have to calculate the firing angle. We are getting firing angle is greater than 90 degrees now. Then that is the correct answer. During the power is delivered from load to source, alpha must be greater than 90 degrees. In this also, I am getting 120 degrees. That 120 degrees greater than 90 degrees now. That is your correct answer. This problem you have to practice. This I am giving practice purpose. Same model. This model only you have to practice. Power is delivered from load to source. You have to find the what is the firing angle. Next. And one more important configuration of single phase full wave or fully controlled rectifier is, that is a bridge rectifier with RL and freewheeling diode and RLE and freewheeling. I told already, RL and RLE same waveforms and same formulas, only I naught form. RL and freewheeling diode V naught by R, RL and freewheeling diode V naught minus E by R. These conduction angles that you have to concentrate. Each SCR conduction angle is pi minus alpha. Freewheeling diode conduction angle is 2 alpha. This is very important. And this is the waveforms. You don't expect any questions from the waveforms. But here the source current waveform is quasi waveform. Source current is the quasi square waveform. With freewheeling diode. Full wave rectifier with freewheeling diode, the source current is the quasi wave. And one more statement, friends, that I repeated so many times. With freewheeling diode, most of the formulas are similar to R load. But only difference is current related formulas will change. The peak inverse voltage is Vm. Circuit turn off time. This is also important. Even the with freewheeling diode, here circuit turn off time is not pi by omega. It is pi minus alpha by omega. Each SCR conduction angle is pi minus alpha, students. If freewheeling diode is not present in full wave rectifier, what is each SCR conduction angle? That is pi. But here pi minus alpha. What is the freewheeling diode conduction angle? 2 alpha. This is important. In half wave rectifier, freewheeling diode conduction angle is pi plus alpha, students. But in semi-converter and full wave rectifier, the next section that I will discuss the semi-converter. In semi-converter and full wave rectifier, freewheeling diode conduction angles are 2 alpha. What is the average output voltage? With freewheeling diode, the average output voltage is similar to R load formula. In full wave rectifier R load, what is the average output voltage? Vm by pi into 1 plus cos alpha. Here also Vm by pi into 1 plus cos alpha. This is the average output current for RL and freewheeling diode. If it is RLE, then you have to use the V naught minus E by R square. This is RMS output voltage expression. But it is a continuous mode. RMS current equal to average current. In a continuous mode, output power equal to V naught into I naught. Input power factor equal to V naught into I naught by Vs into Is. The source current is quasi square wave. With the freewheeling diode case, the source current is quasi square wave. Then what is the RMS value of source current? That is Is I naught into square root pi minus alpha by, because it's a quasi waveform. In quasi square waveform, in one cycle only 2 into pi minus alpha angle only current is exist in the source. That's why this is very important formula, directly you have to remember. The RMS source current equal to, if it is a square waveform, Is equal to I naught. But here Is is not equal to I naught. Here Is equal to I naught into square root pi minus alpha by pi. What the average thyristor current? Amplitude into how much angle thyristor is conducting? Pi minus alpha by 2 pi. If you want RMS, take the square root. What the average freewheeling diode current? How much angle freewheeling diode is conducting? 2 alpha. Conduction angle by total. One cycle angle. That is I naught into alpha by pi. But the RMS value of freewheeling diode current, I naught into square. Every formula is important, friends, that you have to concentrate. And one more important observation that you have to concentrate. Generally, full wave rectifier means two quadrant converter. Which quadrant? First and fourth quadrant. Generally, full wave rectifier, it is a two quadrant, no doubt at all. This is the special case. Single phase full wave rectifier with freewheeling diode is given. With freewheeling diode, the output voltage formula is similar to R load. Then it is operated only in the first quadrant. You take any firing angle less than 90 degrees or greater than 90 degrees, you substitute. Always V naught positive, I naught positive. It is the first quadrant, it is used only motor. Very important, students. The question is asked like this. A full wave rectifier is operating which quadrant? First and fourth quadrant. That is the two quadrant converter. Same question I am asking like this. Full wave rectifier with freewheeling diode. Only first quadrant. Only first quadrant. This is the question with respect to bridge rectifier with freewheeling diode. You have to answer what is the average output voltage and output current. With freewheeling diode, similar to R load formula, VMI. Without freewheeling diode, what is V naught? Without freewheeling diode, if it is a without freewheeling diode, what is V naught? V naught equal to 2 Vm by pi cos alpha. This formula I given. If it is a 2 Vm by pi cos alpha, it is first and fourth quadrant. With freewheeling diode, this is the V naught. V naught equal to Vm by pi into 1 plus cos alpha. This model of question also very important that you have to concentrate. Friends, with this, with respect to module 2 rectifiers, that is AC to DC converters, the detailed discussion of single phase, full wave or fully controlled midpoint type rectifier and bridge rectifier is completed. This is about the session. Thank you.